There we go. Hi, everybody. So these are your notes over introducing how it's called the VSEPR molecule structures, creating VSEPR molecule structures. So this is all about how we know the shape that these different molecules are going to be in. Your notes last night talked about how you know the bonding and how many shared or unshared pairs something has with their valence electrons. But this takes it a step further in actually determining what the shape of these different molecules is going to be. So you guys already have this paper that you see here in front of you. This is from your ring. This is on the back of that mole map. So it has the solubility on the top, the mole map on the bottom, and on the back of it, you guys have seen this. You probably didn't know what it was for quite a long time, and that was this VSEPR molecule structures. So VSEPR stands for valence shell electron pair repulsion. So basically, it's the concept behind why things form the shapes that they form. So the idea here is that depending on the shape or depending on how many electrons something has, shared or unshared pairs, will basically create a situation in which these parts of the molecules will be repelled from one another and pushed away. And because of that repulsion, they form different shapes. So the different options that we have available to us is the linear shape, the bent or V-shaped atom. Then you have the trigonal planar, trigonal pyramidal, and the tetrahedral. So those are the five shapes that we deal with. And you guys will determine what the shape is based off of how many shared and unshared pairs of electrons the center atom has in a molecule. So we give you all the different types and we give you the examples, and then we're going to show you exactly how you figure this out. So this first example, beryllium fluoride. All right, we've got BeF2. So first of all, to come up with this valence arrangement, you have to know how many electrons it would have had. So if I look at the periodic table and I count over, beryllium would have 2 valence electrons. All right, so beryllium, put a pin out here. So beryllium has 2 valence electrons. Fluorine has 7 valence electrons, and there are 2 fluorines, so that's times 2. So this would equal 14 valence electrons plus 2, so a total of 16. My valence electrons would be 16 valence electrons. So I put the Be in the middle, and I surround it with my fluorines. I put a bond to each side, and then I fill up the fluorines, 2 on each side of it, and I count up how many electrons that was. So 2, 4, 6, 8, 2, 4, 6, 8. My fluorine has 8. My other fluorine has 8. You'll notice that beryllium in this case does not have 8 electrons. My beryllium here only has 4 valence electrons. However, beryllium is one of those elements that does not have to be the octet. Lithium, beryllium, and boron can have anywhere between 4 and 8 electrons and be happy. So it is fine. So that's how we arrive at this valence structure. Once you're at this valence structure, you have to make sure you know, is this a straight linear shape or is it supposed to be bent? Because chances are when you draw it, you're going to draw it as a straight structure. But just because you draw it as a straight structure doesn't mean it actually is. This over here on the side tells us exactly what we need to have in order for it to be a linear, bent, or whatever the case is. So if something has 2 shared electron pairs, so if this has 2 shared electron pairs and 0 unshared pairs, it will be linear. Notice here, beryllium has 2 shared electrons and no dots around it. As long as there's no dots around it, it will be a linear shape. There's 0 unshared pairs because these fluorines are going to be equal. Their repulsion against one another is going to be completely equal, and therefore it will be straight. Okay. The next one we have is our water molecule. Okay, in your water molecule, you can see we formed this H2O. In order to bond things correctly, this would have had a total of 6 from the oxygen plus 1 from each of the hydrogens, so a total of 8 valence electrons. So this would have had a valence electrons of 8, and we have 2, 4, 6, 8. Okay, the oxygen has 8 on it, and each hydrogen has 2. So you can see here that they have these 2 unshared pairs. So what happens is if you have a linear molecule, okay, so this is our linear molecule here, and they're just kind of hanging out, nothing's happening. The electrons on the outsides are repulsing each other, so they're keeping it straight. What happens is when you add these unshared pairs in, I'm trying to find some little tools to show you. When I add these unshared pairs in, that's what I'm going to put my unshared pairs as these little clips, is that these clips force a repulsion. They push these guys down, and it therefore repels the electrons that are hanging out at the ends. So because those are hanging out at the ends and they get pushed downward, it forms this bent shape, where in the middle here, this would be my atom. That would be what I'm used to looking at. That'd be my shared pair. So these unshared pairs push down my other atoms at the other end of these pins, basically, and it creates this bent shape. The angle in between right here would be this 105 degrees, but it's because these electrons are here that it goes from being linear to being a pushed down bent. These electrons are pushing down my angle. Okay, so the way you know that this is the case is if you have two shared electron pairs, so two shared electron pairs and two unshared pairs on the oxygen. All right, so two unshared pairs and two shared pairs. All right, the next shape is our trigonal planar. All right, in our trigonal planar, what happens is you have, like in this case, we've got boron trifluoride. So in boron trifluoride, boron has 3 valence electrons, fluorine has 7 apiece. So 7 times 3 is 21 plus 3 from the boron. So it would have valence of 24 electrons. So I've bonded each of the fluorines to my boron, and then I've surrounded the fluorines with unshared pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So 24 electrons have been used. Fluorines are all happy. Notice here the boron does not have a full octet because boron, again, is one of those exceptions. It doesn't need a full octet. So this is shown kind of with a T and then one going down. But realistically, it actually wouldn't look quite like that. It would actually look sort of like if like a upside down Y. I mean, it doesn't really matter like the which part is forward, but it would have this sort of triangular effect. It reminds me of if you guys ever watch Back to the Future, like that particle accelerator piece or whatever. So it forms that shape where the angle in between each of these would be this even 120 degrees, but it would be flat. It would be linear. It would be sort of two-dimensional. Okay, there's nothing different about it. All right, so now that would be your trigonal planar. Again, in this case, 3 shared electron pairs, 0 unshared pairs. Then you have NH3, ammonia. Ammonia, if you counted up its valence electrons, so it has 5 from the nitrogen plus 3 from the hydrogen, so a total of 8 valence electrons. I'm only showing you guys the valence electrons just because we're still learning how to do these shapes, and so I'm just reminding you where these come from. So 8 valence electrons for this whole molecule. So we've taken the nitrogen, we've bonded to it the hydrogens. That took up 6, and then nitrogen needs a full octet, so we've added an unshared pair. So therefore, we get this total of 8, and each of the hydrogens only need 2, so everybody's happy. Okay, so just like before, where when we had the bench shape, those electrons came in. When those electrons came in, it forced these guys down. Okay, so now we have this shape happening here. And what happens is these electrons, these unshared electrons, are basically literally hanging out above this piece. So what you get happening, and I don't know if I'll be able to show you guys this very well in the video, is literally a this is not working out very well, but it's a 3-dimensional shape. All right, let me pull this back a little bit. Where these are literally pushed downward. And then these electrons, these other electrons are hanging out above. So they're all hanging out, but they're filling out like the corners of a box, basically. So they're literally 3-dimensional because these electrons have taken them. They would have been flat. So they would have been like this, completely flat on a parallel plane. And then these electrons force them, put the electrons on this side, force them to push them down. So they become 3-dimensional. Okay, basically, it's like sticking out the legs of a tripod. They go from being flat to being curved. Okay, and so it creates this smaller angle of less than 109 degrees. All right, then the last one, and again, that's when you have 3 shared pairs, 1 unshared pairs. And then for the last one, the tetrahedral, carbon had a total of 4 electrons plus the 4 from the hydrogens, so a total of 8 valence electrons. So I start with my center atom, I bond to it all my other atoms, and then I check and say, okay, I've already used 8 electrons, 0 unshared pairs, all things are successful. I'm not even going to show you. I'll show you guys in class what this tetrahedral looks like. But basically, it's 3-dimensional. It's like what I just had going on. I guess I am going to show you 3 pieces, and then you have a 4th one sticking out the top of it. So it creates a 4th leg of a 3-dimensional sort of image in which they all have 109.5 degree difference. All right. So here at the bottom says, always remember that unshared electron pairs take up more space than shared pairs, and double or triple bonds count as 1 shared pair when determining a molecule's structure. So every bond, doesn't matter if it's a single, double, or triple bond between 2 elements, that's 1 shared pair in terms of figuring this out. You guys will always have this table, so it's just a matter of using this table. All right, what I'm going to look at, what we're going to use as our examples this is the worksheet, it's Bashful. Okay, so this is the back side of what you guys got in class today. So this is Pebbles, and the back side is Bashful. So I'm just going to show you guys a couple examples of how you would do these. But what I want you guys to do is you're not going to deal with the polarity. Our next lesson will deal with the polarity. We're just focusing on the Lewis structures themselves, the molecular geometry, and then the bond angles, most of which you're just reading right off of the page. A couple of these are the examples from the paper itself, like boron trifluoride's on there, so I don't want to do that one. But let's look at this one. Let's look at NO2 negative. This is an ion, so you're going to have to remember that this is actually going to, the number of valence electrons will be affected by that. So here, I'm going to keep track of my valence electrons in this box. So nitrogen has a total of 5 valence electrons, counting off the periodic table. Oxygen has a total of 6 valence electrons, but there are 2 of them. Okay, so that equals 12. So 12 plus 5 equals 17. But I have a negative charge, which means I have a total valence electrons of, instead of 17, 18 valence electrons, because 5 from nitrogen, 12 from oxygen, plus this 1 extra guy from my negative, which means once I draw this Lewis structure, I need to make sure that I'll put it in brackets with the charge on the outside. Okay, so I start with my center atom. Because nitrogen, there's only 1 of them, it goes in the center. All right, my first thing to do is put oxygen on either side of my nitrogen. Okay, surround it with the 2, bond them to it. Okay, at this point, I have used 4 electrons. All right, so now what my first step is, I always fill everything up. I put 2 electrons around all of my unshared pairs, and therefore I fill everything up with unshared pairs. And if you've used too many, then you can work backwards. So my oxygen only has 2. I need to have a total of 8. So I have to add 2 unshared pairs to each side. My oxygen, same thing on this side. And then my nitrogen, 2 on the top, 2 on the bottom. So my oxygen has 8, my nitrogen has 8, my other oxygen has 8. Then I count up how many I have. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh no, I've used too many. So anytime that happens, if you use too many, that means you need to take away at least some of your unshared pairs and create another bond. I'm looking for whiteout. I would highly suggest you guys do these in pencil, so you don't have to use whiteout. Miss Ward should have thought that through before she did it. So I've used 20 electrons, which is too many. Okay, if you've used too many electrons, that means that you're going to need to add a double bond somewhere. So it doesn't matter if I pick which oxygen I pick, okay? There will be, obviously, in this case, resonance structures. So I'm going to pick to put a double bond between these 2 pieces right here, the nitrogen and the oxygen. But now, because I've done that, I have to adjust the number of unshared pairs, because right now my nitrogen has 2, 4, 6, 8, 10 electrons, which is too many. So I'm going to get rid of 2 of my unshared pairs here. Again, using pencil would be better than using pen, so you don't have to use whiteout. Okay, so now my nitrogen has 2, 4, 6, 8 That's fine. But this oxygen has 2, 4, 6, 8, 10 as well. So I'm going to get rid of 2 of the unshared pairs on my oxygen. Okay, so you add a bond and then take away those unshared pairs, and then you see if that did the trick. So now I need to count up my electrons. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. So this is a successful possibility for my Lewis structure. Now, there can be resonance structures for this particular one, but this is the one that I chose to draw. It's not complete until I put brackets around it and put a negative. It is that because it has a negative charge. You do have to include that. Okay, in terms of figuring out the molecular geometry, you're only focusing on the middle piece. My nitrogen, we would call this having 2 shared pairs. All right, again, a double bond counts the same as a single bond. So it has 2 shared pairs. It's bonded to 2 things, and it has 1 unshared pair. Now, you will notice that on your sheet here, they don't give you that option. There's 2 shared pairs when it goes from 0 to 2, okay? This 2 is a 2 or a 1. I should have mentioned that before, but I forgot. So this can be a 2 or a 1. So if you have 2 shared electron pairs and 1 or 2 unshared pairs, it is going to be the bent shape. So the molecular geometry would be bent. And therefore my bond angle would be 105 degrees. So all you do is you draw the structure, and then you decide how many shared pairs, how many unshared pairs, and then you find it on your chart, and you declare what the geometry would be. All right, that's it for tonight's notes. If you guys have any questions, please feel free to ask them, and have a great night.